Hello everyone. Okay, let's do another past paper. Who is pumped? I'm so pumped for this. We'll be doing statistics today. I'll be going through the most recent past paper I have found. We're just gonna run through it. Hope everyone's well. Let's do it. Okay, so we'll just run through this paper. Again, like I've said in the previous videos, this is what you should be doing as the exam comes closer. You should be going through full examinations under preferably time conditions, and you should be checking your answers either after you finish the exam or while you're doing it. I do it while I'm doing it because I got to check that I'm doing them right because I'm uploading this to the internet. Okay, well, Jacob. I'm Jacob. Jacob throws. Okay, it's been a while since I've done stats. Let's have a look here. I've got the mark scheme up here on my Mac screen, and also the formula sheet, so the probability and statistics formula sheet. So I'll show you that. So I got this here. These are all the formulas I guess they give you. Also got that normal distribution function, which we'll probably need, and the mark scheme as well. So I'll be checking my answers. Okay, Jacob throws three coins at the same time. The first coin is biased so that the probability of obtaining a head when is thrown, it is 1/3. Okay, so okay, 1/3. Second coin, same thing, biased when he throws a head is 1/4. Third coin is biased, probability in head is 1/5. Random variable x is the number of heads obtained. So x is the number of heads obtained. Okay, so we want to find the probability that x, the number of heads obtained, is 2. So he throws 3 coins at the same time. Okay, so how does he do that? He throws 3 coins at the same time. So we want 2 heads. So the probability of that happening will be what? The probability that he throws. So when he throws them all together, he gets what? A head, and then a tail. Plus the probability that he gets a head, a tail, then a head, because we want exactly 2 heads are thrown to show it's equal to 3/20. Plus what? The probability tail, head. So those are the only 3 ways in which when he throws them, the first coin, because they're different biases. So this is the first coin, second coin, third coin here. So this is like, we could call it head 1, head 2, tail 3, head 1, tail 2, head 3, 1, 2, 3. So the third coin is a head, or you understand what I'm saying. You get it. Okay, so for this one, the head is the first coin is a head, so that's 1/3, times the second coin is a head, that's 1/4, times the third coin is a tail, so that will just be 1 minus this, because the probability of it's either going to be a head or a tail, so the probability of a tail will be 4/5. So times 4/5 plus this first coin is a head, 1/3, times second coin is a tail will be 3/4, times a head is 1/5, plus the last one will be, zoom in a bit, the last one will be 1 tail for the first one, which would be 2/3, right? Because it's 1 minus this. Probability total must be 1 times 1/4 times 1/5. Okay, so put all this stuff in. So 3 times 4 times 5, 60. So this is 4/60 plus this is 3/60 plus this is 2/60. And if it's all good, that should equal 3/20. So 4/60 plus 3/60 plus 2/60, which is 3/20. Okay, so the probability that x equals 2 is equal to 3/20. Cool. Draw up a probability distribution table. Okay, so we're just looking at the different probabilities now. Or if x is 1, x is 0, x is 2, x is 3. Because we've got 3 coins, so the most that x could be would be 3. So we could say x, our value. And this would be the probability that x equals x. So 0, 1, 2, 3. And already to check that this will be correct, we should sum all these up and they will equal 1. We already know this one. This is 3 over 20 when x equals 2. When x equals 0, let's look at these things. My cat. When x equals 0, I'm going to have to shut her out. You can't be here. Look, it's my cat. Put her out because she's just going to keep jumping up here. Okay. When x equals 0, it means there's no heads. So the only way that can happen is if it's probability tail 1, tail 2, tail 3. What is that? That is going to be 2 over 3 times 3 over 4 times 4 over 5. 2 over 3 times 3 over 4 times 4 over 5. Okay, that equals 2 times 2 times 4. This is 24 over 60. Over 60. Simplifies 2 over 5. Okay, the probability that x equals 1. So one head, what can that be? That could be head 1, tail 2, tail 3. Plus you could have tail 1, head 2, tail 3. And finally you could have tail 1, tail 2. Okay, those are the only ways that can happen. So that is going to be, so this is 1 over 3 for head 1 times 3 over 4 times 4 over 5, plus this one will be tail 1 will be 2 over 3 times head 2 will be 1 over 4 times tail 3 will be 4 over 5, plus tail 1 will be 2 over 3, tail 2 will be 3 over 4, and tail 5, head 5 will be 1 over 5. Okay, you add all that stuff up. So this gives us what? 12 over 60 plus, goodness, is 8 over 60 plus 6 over 60. 6 plus 8 plus 12 is 26. This is 26 over 60, or 13 over 30. Okay, and finally we need to find the 3, which is easy because it'll just be, this is just the probability head 1, head 2, 2, head 3, which is just 1 over 3 times 1 over 4 times 1 over 5, 1 over 60. Okay, so we have 0 is 2 over 5, we have 1 is 13 over 30, and we have 3 is 1 over 60. Okay, so just to check, all these things should sum up to 1. So 2 over 5 plus 13 over 30 plus 3 over 20 plus 1 over 60. And it does, that sums up to 1. So all these things sum up to 1, so that means our probability distribution table is most likely, highly likely correct. Okay, finally, given that e of x equals this, find the variance. Well, we're going to need to use this formula. So go to the max screen. Okay, so for discrete random variables, which this is, we have this variance formula here. So we can write that the variance of x equals to the sum of x squared p, which p's are the probabilities, minus e of x squared. So what is this thing here? Well, this is these things squared times these probabilities. So the first one will be 0 squared times 0, but I'll write it out, 2 over 5, plus 1 squared times the second probability will be 13 over 30, plus 2 squared, 3 over 20, and finally 3 squared times 1 over 60. So equals to 13 over 30 plus 4 times 3 is 12, so 12 over 20 plus 9 over 60 gives us what? 13 over 30 plus 12 over 20 plus 9 over 60. So 71 over 60. Okay, so therefore our variance is going to equal to 71 over 60 minus 47, this 47 over 60 squared. This minus 47 over 60 squared gives us 0.5697222. So rounded would be what? 0.57. I guess we'll just round it to that. I still am unsure about how many significant figures they want. I probably should check that. Okay, that's the first question done. Okay, so we will check these. So I'll just look on my Mac. Yeah. Okay. I guess I'll show you. Mac screen. Okay. So 3 over 20, yes. 2 over 5. Yes, yes, yes. And finally 0.570. Yes. Okay, back to the iPad. Okay, so those were all correct. Correct. 1 mark. Got all those. 3 marks. And I got this. Okay, let's move on. Okay. Last year online, an online store sold a large number of computers. 55% of the computers were made by company F, 30% were made by company G, and 15% were made by H. Okay, a random sample of 3 customers who bought a computer from the store is chosen. Find the probability that the 3 customers bought a computer all made by different companies. Okay, so let's just write this out. So the probability that it was bought from F is 0.55. The probability that it was bought from G is 0.30, and the probability it was bought from H is 0.15. Okay, so we have a sample of n equals 3. So 3 customers who bought a computer from the store is chosen. Find the probability that 3 customers bought computers all made by different companies. Okay, well this is just the probability. If they're all made, well these 3 things that they bought, so the probability, let's say different, is going to be the probability of F times the probability of G times the probability of H. So that's 3 different scores. But however, these can be arranged 3 factorial ways. So you can arrange these because they could purchase one of them. Let's say this is the first customer, second customer, third customer. Well, the first customer could be buying from H, or the first customer could be buying from G. So it's also arranging these things by 3 factorial. So we have to multiply by 3 factorial. There's 6 ways we can arrange these probabilities because there's six different ways that each one is different from all 3 customers are different could happen. So that's why you do that. So this would be 0.55 times 0.3 times 0.15 times 3 factorial, which is 6. Okay, so it's 0.55 times 0.3 times 0.15 times 6. That gives us the probability of D 0.1485. 0.1485. I guess I'll just leave it like that. Okay. A random sample of 12 customers who each bought a computer from the store. So now our N is 12. Find the probability that fewer than 10 of these customers bought a computer made by company F. Okay, so the probability F is what? 0.55. Okay, so this is binomial because we have a success and a failure. So the probability of success is 0.55, which means they bought from company F, and the probability of failure, so let's call it F, well, let's call it Q. I think they call it Q, is 1 minus this, which is 0.45. And our N is 12. Let's go over to this binomial formula, and we have this binomial formula here. So I'll write that down. So PR equals N R PR 1 minus P, which is the failure. Okay, go back to math. Okay, so this is our binomial formula. This is what we want. So X is the number of customers who bought F. Okay, so we want the probability that X is fewer than 10, is less than 10. So you could calculate the probability that X equals 0 plus the probability that X is 1, 2, 3, all the way up to 9. Or you can just do 1 minus, because it's 12, the probability that X is greater than or equal to 12. Because that would be the same thing. Right? Because the total sum is going to be 1, all those probabilities. Okay, so this thing equals 1 minus, we just substitute this stuff in. So this would be the probability that X equals 10, plus the probability that X equals 11, plus the probability that X equals 12. Okay, and that would be 1 minus, what is this? So 10. So we have 12, 10. The probability here is 0.55 to the R, which is 10 successes, times failure, which is 0.45 to 2. Let me just basically iterate through this. 12, 11, 0.55, 11, 0.45, 1 plus 12, 12, 0.55, 12 times 0.45 to the 0, which is just 1. It's 1. Okay, so this is going to be equal to 1 minus, what is this stuff? Well, so to do this this thing here, I don't know if you can see this, it's this combination thing on your iPad, I mean on your calculator. So this, I'm just going to write this out again. So 66, I'll just plug it all in. No, okay. I want to get an exact value. So this thing here was 66. 66, 0.55, 10, 0.45 squared, plus 12 combination. I'll just rub it out here. Just don't have enough space. Okay, so I'm going to calculate these things here, this thing. So this is 66, that value. And 12, 11 will be 12 combination 11 is 12. And 12, 12 is 1, but I'll just double check that. 12 combination 12 is 1. So that's 1. That's just gone. This thing, anything to the power of 0 is 1, so that's gone. Okay, so now we can just plug all this stuff in. So 66 times 0.55 to the power of 10 times 0.45 squared plus 12, 0.55 to the power of 11 times 0.45 plus 0.55 to the power of 12 gave me this gave me what's this? 66 seems too small. 0.55 to the power of 10 times 0.45 squared and 66. You gotta be careful with these things. I might just write those things out. So we got 0.03385 plus 12 times 0.55 to the power of 11 times 0.45. 12 times 0.55 to the power of 11 times 0.45. God, that's so small. 0.55 to the power of 11 times 0.45 times 12. So plus 0.55 to the power of 12 plus 0.3385. Plus 0.033385. 1 minus answer. Okay, this is what I got. If you put all that stuff in, you should get 0.9578 ... The probability that x is less than 10 will be 0.958. I guess we can round it. Okay. Let's keep going. A random sample of 140 customers who bought a computer from the store is chosen. Use a suitable approximation to find the probability that more than 24 of these customers bought a computer made by company H. So the probability of H is what? 15%, 0.15. Okay, so this is binomial, so we have the probability of success, 0.15, and the probability of failure will be 0.85. So the suitable approximation, because it's such a large sample, because our n now is 140, the suitable approximation is normal. So we are approximating this binomial, which is with 140 and our failure. I'll just write it out like this. So this is, I'm just looking at the formula sheet. So this is NP. We're approximating this to a normal, which is, they do it like mean and variance. Okay, so to do that, so I'll just go to the Mac screen. Okay, so we have this is binomial. It's a binomial distribution of this variable x. So if we want to find the mean and variance of this, we use those formulas. So I'll write those down. NPQ. The iPad. Okay, so this is what we have. So we have this situation which is binomially distributed. It's a tough word. And we're approximating it to a normal. So we need the mean and variance of that approximation based on the data that we have. So x, so our mean is going to be 140 n times 0.15, which equals to 140 times 0.15 is 21. And our variance is 140 times 0.15 times Q, which is 0.85. So 21 times 0.85, basically, times 0.85. So 17.85. Okay, so this is our approximate 21, 17.85. And we want to find the probability that is more than 24. So X is more than 24. But in fact, because we're approximating it, like if you think about it, I remember I have a video on this. Like if this is our normal distribution and we're approximating this discrete binomial distribution. So like this 24, this is 21, like this 24 value here is kind of, you can visualize it as like a bar. I remember teaching this before. And so this point here, if we're looking for 24 or above, that's a discrete value. So 24 and above will actually be 24 on this distribution will be 24.5 because it's half of this. So 24 above 24 will be half of this. Because we're looking for that entire, like above this bar, if that makes sense. Like we're looking for above this line here, which is 24.5, where this bar ends. So more than. So actually, so for this approximation, we'll need to find this. And that's the little, like, I think that's why this thing's worth 5 marks. So now we just solve this with a normal distribution, but for 24.5. So our z value, remember the z value is x minus mu over the standard deviation, which in this case is 24.5 minus, so we're standardizing the curve, minus 21 divided by this thing, the square root of 17.85. So that's the variance. Okay, so therefore the z value will equal to 24.5 minus 21 divided by the square root of 17.85. So this gives us 0.0828. Okay, so the probability that x is greater than 24.5 is equal to the probability that the standardized curve is greater than 0.828. And that, if we look at this, this will be 1 minus the probability, because we're going to need that with the table, minus this. It's the same thing. And this thing from our table is notated like this. I'll show you that on the screen. Okay, max screen. Okay, so we go to our table here. So these are calculating, so you should have studied this thing, but these are calculating this area. So if we look at our we have 0.828. So z value 0.82, 82 and 8. You go across here 8, so you're adding 22 to this. 0.82. So this thing here, this value 0.82 added 22 will give us, so 0.79, so 39 plus 22. So this is 0.7961. So from that table, this gives us the area. So looking at 0.828 is the answer is 0.7961. So I added 22 to that 39 at the end there. Okay, let's go back to the max screen, the iPad. Okay, so this is equal to 1 minus, this thing looked up on our table was 0.7961. So 1 minus 0.7961. So this gives us 0.2039. So rounded, I guess you could say the probability that x is greater than 24, because that's what it's asking, but we did all that standardization and approximating or whatever, is 0.20, let's say 204. Okay. Right, let's check this stuff. Let's go to max screen and let's check this stuff. Okay, the first one was 0.1485. We got that. Next one was 0.958. We got that. And the last one was, see, they did the same thing, was 0.204, and we got that. Cool. Okay, go to the iPad. Okay, so we got all this stuff. So correct, and correct. There's 5 marks because using that approximation, you have to remember to do this. Otherwise, it's just a binomial thing. And if it was less than, like going less than this thing, you know, you would take 23.5. I think I went through that in my normal distribution videos. I've gone through it already. Okay. The length of leaves of 250 leaves of a certain type, a plant are measured correct to the nearest centimeter. The results are summarized in the table below. Okay, so the frequency of them being between 5 and 9. Okay. On the grid below, draw the cumulative frequency graph to illustrate. Okay, so we're just adding up these frequencies. Okay, so we need to do a cumulative frequency distribution. So the cumulative frequency, we go less than, so you want to take between 9 and 10, between 14, so less than 9.5, less than, the next one will be less than 14.5, the next one will be less than 19.5, the next one will be less than 24.5, and the last one 29.5, and then finally the last one will be less than 39.5. 39? I guess 39.5. Okay, so the first one is 18. Then it's cumulative, so 18 plus 28. So we just add these things. So 18 plus 28. 18 plus 28, 46. Then what is this? 20. So 46. What? Plus 60? No. 46. So we have 18 here, then 28. Then we have 60 here, so it's a free. So it's 18 plus 28 is 46. So then 46 plus 60 is 106. And then to this one, we add a frequency, because frequency is plus 72 is 178. And then plus 48 is 226. Okay, so it's cumulative frequencies, accumulating. You're adding them together, the frequencies. And then this last one plus 24. Plus 24. 50. Okay, so now basically all you do is graph this thing. Whatever this thing is. Just graph this thing. So you need to pick an appropriate scale. So I guess we'd have length here, centimeters. And this would be your cumulative frequency. Ugh, I don't want to have to graph this, but I will. So what? 20, 40, 20? 20, 40, 60, 80, 20. We're going to need above 250 here, so maybe 40. So 40, so this one, 40, 80 at each of these points, 80, 120. I'm picking an appropriate scale. 200, because that gives us 240, 280. Oh, because that gives us, okay, 250 will be here. So each square here, so we could write this as a no, each square here would be 40 divided by 10, which is 4. So each one of these little squares is 4. That's probably going to help us. And then on the bottom, I guess you could just say 10, 20, 30, 40, 50. Yeah. 10, 20, 30, 40. You just need to 40. That's fine. That's 0 on both. Okay, and we just plot these points. So you have to plot like 9.5. Okay, so 9.5. So this is 9.5. So it'll be here. And this is 18. So 18. So I'm just going to 18 divided by 4 to see how many squares I go up. 18 divided by 4 is 4.5. So this is 9.5 here. And 4.5 is here. So the first one is going to be there. Okay, and then 14.5 is here, and then 46 divided by 4 is 11.5, so we go up 10 squares, 11 squares, 0.5, so 10, 11.5, so that's here. Okay, 19.5 is here. And then 106 divided by 4. I divide by 4 because I want to know how many squares. So this is 26.5 squares. So 106 divided by 4 is 26.5. So I go up 10 squares, 20 squares, 5, 6 squares, 0.5. So 26.5 is here. And then 178 divided by 4. This is 44.5 squares. At 24.5, so 24.5 is here in the middle. So then we go 10, 20, 30, 40. So 10, 20, 30, 40, 44.5. 44.5 is here. And then 29.5 is here. And then we have 226. 226 divided by 4 is 56.5. Okay, 50, so 10, 20, 30, 40, 50. 56.5 is here. And then finally the last one is 39.5, which is here. And 250, so 250 divided by 4, 62.5. 1, 2, 3, 4, 5, 6, 62.5 is here. Okay, and I guess you could kind of like sketch this thing out. It goes from 0 to here to here. It's poorly drawn, but whatever, you get the idea. Okay, so it looks kind of like that. And that's it. Okay, B. 38% of the leaves are of length K. Use your graph to find an estimate for K. 38% of the leaves. So cumulative, so it'll be 60, so 1 minus 100 minus 38, so 62%. So 62. What am I doing here? 62. So 250. So we have 250. 30% leaves of K centimeters or more. Use your graph to find an estimate for K. So K or more will be 38% of the leaves are K or more. So we need to look at 62%. So 62%. So basically you want to find 0.62 times the total amount of cumulative frequency of leaves is 250. That would be okay. Well, that will be 0.62 times 250. This is 155. So that's going to give you the cumulative frequency point. So how many frequencies are more than K, you know, or like you get, so you go to like 155. This would be what? 155 divided by 4. 38, oh god, 38.75. 10, 20, 38, 75. So this point here is 155. And then you trace this thing across and it hits around here. So that's why I probably should have drawn it better. So, I mean, that's roughly what? 1, 2, 3. So it's roughly around 23. So K centimeters, or leaves that are A length or more, will be K will be roughly 23 centimeters. Okay, calculate an estimate for the mean length of 250 leaves. Well, this will just be, you find the halfway midpoint between these things and you multiply them by the frequency. So it's just that mean formula. So the mean is, you know, the sum of these x values divided by n, the total, which will be 250. But the sum of these x values will be, so therefore m equal the sum of these x points. So you're going to need to look at the midpoint. So let's just do that first. So the midpoints of these kind of ranges of these frequencies, you know, it's going to be 5, between 5 and 9. So 5 plus 9 divided by 2. So the, 5 plus 9 divided by 2. So the first one, so this, I guess I could just write it up here. So the mid points is 7. 10 plus 14 is 24. So this divided by 2 is 12. 15 plus 19 divided by 2. I'm just finding the midpoints, the midpoint of this range, because that would be the mean. 20 plus 24 divided by 2, this is 22. 25 plus 29 divided by 2 is 27. And 30 plus 39 divided by 2 is 34.5. Okay, so our midpoints are 7, 12, 17, 22, 7, 12, 17, 22, and 27, 34.5, 27, 34.5. Okay, so the mean will just be the sum, which will be 7 times the frequency of that occurring is 18. 18 plus 12 times 28. 28 plus 17 times 60. 60 plus 22 times 72. 72 plus 27 times 48. 48 plus 34.5 times, no way go dark, times 34 times 24. 24, and that entire thing divided by the total, which is the n, the total cumulative frequency, is 250. Okay, and so we plug all this stuff in. 7 times 18 plus 12 times 28 plus 17 times 60 plus 22 times 72 plus 27 times 48 plus 34.5 times 24 divided by 250. This gave me 20.76. It's 20.76 20.76 centimeters. Okay. Okay, so I'll quickly check these things on here. Mac. Okay, my graph looks extremely similar to that. I'm not gonna bother checking it deeply. 23. So K is 23. Okay, got that. And 20.76. Cool, got that. Okay. back. Okay, got that. Got that. Okay, let's keep going. Eddie has 16 toy cars. Do you, Eddie? Do you have 16 cars? Well, I've got 17. So deal with that. Of which 8 are white, 5 are black, 3 are silver. Okay, cool story, Eddie. He places all the cars in a bag and selects 3 of them at random without replacement. Ooh, without replacement. Find the probability that all 3 cars are the same color. The probability that all cars are the same color. How can that happen? So he selects 3 of them at random. So 1, 2, 3. So he's picking 3. So the probability they're all the same color is, so it could be white 1, white 2, white 3, plus probability of black 1, black 2, black 3, plus the probability of S1, S2, S3. So 3 silvers, 3 blacks, 3 whites. So the only way they could be all the same color. Yeah, I don't see why that wouldn't be right. Just thinking if they're trying to trick me in any way, because that seems just a little too easy. So the probability of white is 8 over 16. It's half. Probability of black is 5 over 16. And the probability of silver is 3 over 16. Okay. Without replacement. So when you take one, that one's gone. Okay. So this is going to be, well, the first one, the probability is going to be 8 over 16 times the second white one, because you've taken one white one out. And then, so now you only have 15 of them. And 7, so this would be 7 over 15, right? Without replacement, yeah, times 6 over 14. Right, we've taken one white one out, so now there's only 7 whites left. 7 whites left, and 15 balls left. Okay, yeah. I would assume it's that. That's why it's 3 marks. Okay, so the black one will be 5 over 16 times the black 2 will be 4 over 15 times 3 over 14. And then finally, plus the last one will be still 3 over 16 times 2 over 16 times 1 over 16. Oh no, sorry. Over 15 over 14. Right, because one's gone. One white's gone. So the probability is it's getting less. Okay, so this is going to be, what's 16? 16 times 15 times 14. 360. So 360. 8 times 7 times 6. 336. That plus 5 times 4 times 3. 60 over 360. Plus 3 times 2 times 1. 6 over 360. So 6 plus 60 plus 336 divided by 360. 0.1196 dot dot dot. So the probability all the same. So let's round it. 0.120. Again, I'm unsure about this rounding. I think that's right. Okay. B, find the probability that when 3 cars are selected, at least 1 car is white and at least 1 car is black. And 3 cars is at least, okay, so how can that happen? So the probability that at least, so at least 1 car is black and 1 car is white, at least 1. So these two, the probability that 1 black and 1 is 1 black and 1 white, at least. So how can that happen? You could have at least, at least. No, so it's greater. All right. Yeah. Okay, so how can this happen? So we can select a black one, a white one, and a silver one. Black one and white one and silver one. Plus black one. Would it matter if I do white one, black one? Is he select? Select 3 of them at random without replacement. It would matter what order he selects them in. Right, because it's going to change the probability. So a white one, a black one, silver one. Plus, it's 4 marks. Plus a black one. I guess we could just do how we arrange it. Yeah, I guess we could just do that. So it'd be a black one, a white one, a silver one. Plus a black one, a white one. One black one, one white one. A white one. A black one, a white one. Yeah, plus is that gonna matter? I just don't understand. So that when the 3 cards are selected, is this when he's selecting in order? Find the probability that all 3 cards are the same color. He places all the cards in a bag and selects 3 of them at random without replacement. Does he select 1, 2, 3? Plus the probability of black one, a white one, a black one. This one has at least 2, at least 2, at least 2. That's the only way it can happen, right? Times the amount of ways. So this one will be times 3 factorial. So it doesn't. Yeah, because you can select silver first. Yeah, because it's not different. Yeah, okay, this will work. Times this one will be 3 factorial over 2. Right, because that's the amount of ways, because it doesn't. He could select the white one first and then the black one, or the white one first and then a white one and then a black one. We're just arranging that because there's 2 white ones. They're considered the same thing, right? Times 3 factorial over 2. Right, so this thing will be a black one is 8 over 16. 8 over 16 times a white one is 5. So this would be what? 5 over 15, because now we've taken one, times silver one will be 3, because we still have 3 silver, over 14. Right? Yes. Okay. Plus black one is, and then this thing times 3 factorial, which is 6, because it's the amount of ways we could do it. We could do this one first or this one first, and it will be different. Times that plus this one will be a black one, which is 8 over 16, times a white one, which is 5 over 15, times another white one, which would be 4 over 14, because we've taken one white one out, times 3 plus black one, 8 over 16, times a white one, 5 over 15, plus another black one, which would be 7 over 14, times 3. Okay, so that's going to be what? 16 times 15 times 14. So this is going to be 8 times 5 times 3 times 6. This is 720 over 3, 360, plus 8 times 5, 8 times 5 times 4 times 3, 480 over 360 plus 8 times 5 times 7 times 3 is 840 over 360. 40 plus 480 plus 720 divided by 360. This is probability of this happening will be 0.607. Just gonna think about this for one more second. Find the probability that when the three cards are selected, at least one card is white and at least one card is black. So these are the three situations in which that could happen. And then we times this by these because the order, we're it's a sense of overcounting the probability because the order we're timesing by, okay, because we could also, we're undercounting, that's why we're timesing, because this B could be here, or this B could be there, this B could be there. Well, it doesn't matter if the two B switch because they're the same, but like we overcount, so we times by that thing. Okay, that should be correct, I think. Let's check that. Let's go max screen. Okay, let's check this. Okay, 4A 0.120. Okay, that's correct. First one was correct. Yeah, okay, so I did it right. So it's that, it was that not without replacement, which was kind of tricky with that. And this one, oh god, 0.607. Yes, I got that. Okay, cool. Okay, is that how they did? They did the same as me? Yeah, they did the same way. Two methods, okay. Okay, so yeah, this one was a little bit tricky. Okay, let's continue. How many more do we have? 5, 6. Okay, two more questions. The mass of peaches sold per day. The mass of peaches sold per day in a supermarket is normally distributed. Okay, so this is it. Our mean is 65.8, and our standard deviation, so this variance here will be 9.6 squared. Okay, find the probability that the mass of peaches sold on any given day is between 56 and 75. So we want the probability that X, so X represents the mass of peaches sold per day. So the probability that this is between 56 and 75. Okay, so I always like to sketch this thing out. So we have, it looks like this. So our X, this thing here is 65.8. So 56 is here, 75 is here. So this thing. Okay, so the probability that it's between these two things, 75, is equal to the probability that X is less than 75, this thing, minus the probability that X is less than 56. Okay? Right, because it would be less than 75 minus this bit, less than 66, would give you this inner bit here. Okay, so now we need to standardize this. So our Z standardization, just say Z values, will be, Z1 is, remember this is X minus mu over this. So this is 75 minus 65.8 over the standard deviation, which is 9.6. That equals to 75 minus 65.8 divided by 9.6. So that is 0.958. And Z2 will be 56 minus 65.8 divided by 9.6. So that is 56, which is negative, which makes sense for the z distribution, minus 65.8 divided by 9.6, this is minus 1.02. 1.020 1.02 rounded to that because I know 1.021. Okay, so the z distribution, this is our z2 and this is our z1. So it has to be, so we want the probability that is between minus 1.021 z and 0.958. That equals to, again, the same concept, will be the probability that z is less than 0.958 minus the minus the probability that z is less than minus 1.021. However, with this z distribution, because it's about 0, we can say that this thing, you know, if this is this z2, if we want this area is the same as saying, because this is minus, this is minus 1.021. This is positive 1.021. It's symmetric. So we can say that this thing is going to be equal to, this thing here will be minus 1 minus this area here. So minus the probability that z is less than 1.021. Right, because that will give us that bit here in the middle, this bit here, right, for this last part. So really we want to find the probability that z is less than 0.958 minus will be plus the probability that z is less than 1.021 minus 1. And these values can be found from our table. So 0.958 plus 1.021 minus 1. So then we go to our Mac screen. Yeah. And we look at our table. Okay, so 0.958. So the z value is 0.95. So this 0.958, add 20 to this. So this first one is 0.82, or add 20 will be 0.8309. 309 plus 0.958. That's correct, right? 0.958 plus 1.021. 1.021 add 2. So 0.8461 add 2. So 0.84. No, 0.8. So 1.021. 1.02. 0.8461 add 2. So 0.8463. 0.63 minus 1. Okay, so I just went to those and found these values here. So if we plug this into our calculator, so 0.8309 plus 0.8463 minus 1. So so this gives us 0.6772. So the probability of this 56x and 75 is equal to 0.677. I guess I could just round it to that. It's fine. Okay. Keep going. Much more. The mass of cherries sold per day in the supermarket is normally distributed with a mean of, okay, so we've got a different one, and a standard deviation unknown. it is known that on 10% of the days less than 59.1 cherries are sold. So we've got this distribution. It is known that on 10% of the days less than, so 59.1, this is 10%, so this is 0.1, 72.4. So this is our, you can call it a new, let's call it Y. So our Y is mass of cherries sold day. Okay, find the standard deviation. Okay, let's think about this. So we know that the probability that Y is less than 59.1 is equal to 0.1. So what's the corresponding Z value for that? So Z equals to 72.1 mean minus 59.1 over gamma, or standard deviation. So this thing, which is what? This thing is 72.4. 2.4 minus 72.4 minus 59.1. This is 13.3. Okay, so if we look at this, so this thing, which is, let's call this Z1, this Z1 here, I guess this thing will be negative. So negative Z1 here. Will it be negative? Should be negative. Oh, I did it the wrong way around, that's why. Okay, x is x minus mu. I did mu minus x. So this is 59.1 minus 72.4. So that's minus, which makes sense. Okay, so this thing here, this area here is 0.1. So if we say that the probability this is less, I'm doing all this because I'm trying to get an equation for the standard deviation, is less than, so if Z is less than Z1, or Z1, this equals 0.1. But if we want to find that on our table, we'd have to say it'd be 1 minus this thing, oh my god, this thing equals 1 minus this, less than Z1. Z1 is negative, right? Yeah, so this thing is negative. So this would be less than Z1. Minus Z1. To make this thing positive. This thing equals to 1 minus that would be 0.1. Or you could say this thing Z1 this is our Z1 minus, this is a fucking bad way to explain it, equals to that thing, which would be, god, why do they give us no freaking space? Like, it's so annoying. Just the minus sign is tripping me out. I'm just going to keep it like that. I'm not going to make it less general. 13.3 over gamma. So this thing is minus 13.3 over standard deviation. This thing equals to 13.3 over this. 1 minus that gives us the same area. So this thing will be 0.9 of 13.3 over gamma. So this thing is 0.9. So we can find this value. So this corresponding z value, which we called z1, this corresponding z value is 0.9 on the graph. So if we go to our Mac screen, we go to, what is an area of 0.90? So we want an area. So this area gives what z value? That's what I'm asking. So 0.9, where's 0.9? 0. Yeah, so this 1.281 1.281 will give 0.9999, which is as close as I can get. So 1.281. So I'm just going to draw that down. 1.281. Okay. Okay, so the z value, which gives an area of 0.9, is equal to 1.28281 from our graph, from our table. So that means that therefore we can say that 1.281 equals to this, equals to 13.3 over gamma. So our standard deviation will be 1.281 divided by 13. 0. That seems wrong. That's too small. If I looked at the z value wrong, what have I done wrong here? The corresponding z value, give an area of 0.9. 0.9. What have I done wrong here? 1.282 1 times gamma. Oh yeah. Gamma equals will equal to 13.3 divided by 1.281. Oh, why did I'm fatiguing. 1.281. 10.4. So this gives gamma, standard deviation is 10.4. Okay, sorry, that was bad. That was a bad explanation. All right. I just wanted to find out. I found we were given this area, so I found the corresponding z value for that area. I then found on the table what would give this area. And then when I found that, I can plug this thing back into here and find this. Anyway, that probably took way too long. Okay, let's keep going. I want to finish this. This is getting a bit fatiguing now. The supermarket is open 7 days a week. Find the probability that in a randomly chosen week, the first day on which less than 59.1 of the cherries are sold is the 5th day of the week. Oh god. Okay, so the probability that the cherries are sold is what? 0.1? The probability that they're less than 59.1 is 0.1. So this is 0.1. So that's the probability. So on any chosen week, the first day on which there's less than 59.1 of the cherries sold, so the first day in which this occurs is on the 5th day. So that would just be the probability. So we have no cherries on the first day, less than this, no cherries on the second day, less than this, no cherries on the third day, less than this, no cherries on the 4th day, less than this, and then cherries on the 5th day that are less than this. The mass is less than this. So these ones are just, 1 minus that. So 0.9 to the 4 times 0.1. So just be that. 0.9 power 4 times 0.1. So 0.06, 0.0. 656. So probability is equal to 0.0656. Still need to check all this crap. Please don't be wrong. Okay, okay, last one for this question. Find the probability that in a randomly chosen week, first day on which the cherries, which are less than 59 cherries are sold, is before the 5th day. Before the 5th day. So this day of cherries that are less than 59.5 is, this day is less than 5 out of the week. It's on the 5th and less than 5. So wait, of the cherries are sold before the 5th day. So this, which represents the number, the days in which these number of cherries, the mass of cherries is less than 59.1. This, which could be the same as 1 minus the probability of no cherries less, so niggly, less than 59.1 kgs are sold in 4 days in a row, right? Because this probability, okay, there's no cherries less than 59.1 on the first day, second day, third day, fourth day, fifth day. 1 minus that will give us this. So 1 minus this, which is no cherries sold on 4 days, is just 0.9 to the 4. Okay, so just such a stupid question. 1 minus answer. 0.34344. So probability x is 5. I didn't specify what that is, but it's fine. Okay. Alright, let's check these things. So the first answer we got was 0.677. The second answer was 10.4. Let's check that. Max screen. So the first answer was 0.677. What's this? Boom, 0.677. First one's right. I'm getting over this. B, 10.4. We got that. C, yeah, exactly what I did. 0.0656. Cool. And the last one, 0.344. Cool, we got all those right. Okay, let's give me some text. Boom. 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 God, some of these questions in the statistics are just like, oh, for what, dude? Like, what? When am I going to need to calculate crap like that? I don't know. It's so stupid. Oh, and then this stuff again. This is the combinations and permutations question for sure. I can see it already. This is some stupid. Okay, no, I won't say that. Okay, let's just take. Hold up. I'm just gonna do this and we're done. Oh, it's gonna be difficult. I can feel it. Elisa has 10 different books from the series Squares and Circles. The books are similar except for their color. 3 blue books, 2 yellow books, 1 orange book, 1 purple book, and 1 green book. I'm just gonna write that out. So we have 1, 2, 3 blue books, 2 red books, 2 yellow books, 1 orange book, 1 purple book, and 1 green book. Exciting stuff. Elisa places the books in a row on herself. She is only interested in the arrangement of the colors. Okay, how many different color arrangements are there of the 10 books? Okay, we have 10 books. This would be 10 factorial, the number of ways we can arrange this 10 objects. We have to divide by, because she only cares about the colors, if we exchange these blues position, well, it's the same arrangement. So we divide by 3 factorial and also 2 factorial for the reds and 2 factorial for the yellows. That's that. So 10 factorial divided by 6 divided by 2 divided by 2. 151,200. Okay, good luck arranging it that many times, Elisa. Okay, how many different color arrangements are there of the 10 books in which 3 blue books are together but 2 yellow books are not next to each other? Okay, I remember how I used to do this. Okay, we go. Okay, so we got these B1, B2, B3. These things have to be together, so they're in a singular slot. We have another slot. Then we have these space slots. So then we have these red book, or these objects, which can be arranged any way we want. Because the blue books have to be together and the yellow books can't be together. So we extract the yellow books out. So then an orange book, a purple book, and a green book. Okay, so 3 blue books are together, but the 2 yellow books are not next to each other. Okay, so how many ways can we put, so we have these 2 yellow books which can't be together? I've got a video on this. So we put, how many options do we have for the first? So let's say if we put it here, what I'm saying is if you put the yellow one here, then the yellow 2 here, the arrangement would be yellow 1, these blues, yellow 2, red, orange, purple, green. Okay, so we could put the yellow one here. 1, 2, 3, 4, 5, 6. Wait, 1, 2, 3, 4, 5, 6, 7. There's 7 spots for the first yellow one. But then for that selection, for that arrangement, there's then 6 slots for the next one because we've taken one of the slots. Okay, so for this thing, so 7 times 6, we're putting those things in this setup which I'm providing. And then we can arrange these objects around that yellow selection, which is like 7 times 6 different things. We can do that 1, 2, 3, 4, 5, 6, 6 factorial, 6 factorial, 1, 6 factorial, 6 factorial, 1, 2, 3, 4, 5, 6, 6 factorial divided by, we're treating this as a singular object because the 3 blue books have to be together, divided by 2 factorial because red 1 exchanged with red 2 is the same arrangement. So that would be it. So total would be 7 times 6 for placing these things in, times 6 factorial with 2 factorial. Is that making sense? I'm saying that if you put yellow 1 here and yellow 2 here, the arrangement would be B1, B2, B3, yellow 2, red 1, red 2, orange, purple, green. If you put this one here and this one here, then that would be the arrangement. If you did it different, if you put, let's say, the yellow one at the end, well then you would take that yellow 2 out and you would put it here. Yellow 2 and then your green would be there. Okay, and that's another arrangement. So I'm just setting it up in a manner, the structure of how I've set it up, so the yellows are never together and the blues are always together. Okay, so this is the final thing. So, and also you'd have to divide this by 2. Yes, because you divide this by 2 because if I put yellow 1 here and yellow, let's say yellow 2 here, well, if I put yellow 2 here and yellow 1 here, it's the same arrangement because it's color. So I'm just identifying the difference. Yellow 1 and yellow 2 are the same. So you divide by 2 because we're over counting. So 7 times 6 divided by 2 times 6 factorial divided by 2. So this is 7,560 ways. So total 7,560 ways. Okay. Okay. Take 1, 2. Okay, 2 more questions. Come on. How many different color arrangements are there of the books with exactly 4 books between the 2 yellow books? Oh my god. Okay, we have, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 slots. We want exactly 4 books between 2 yellow books. Yellow 1, yellow 2. Okay, so if I place the yellow one, let's say if I place it here, there must be exactly 4 books between them. So if I place yellow one in this slot, so this is the 10 slots of the 10 books. If I place the yellow one here, then 1, 2, 3, 4, the yellow 2 has to go here. So if I place the yellow one here, the yellow 2 has to go here. If I place the yellow one here, then yellow 2 has to go here. And so on and so forth. If I place the yellow one here, is it yellow one here? 1, 2, 3, 4 can't go there. 1, 2, 3, 4. So the yellow 2 has to go here. Okay, so how many ways can I place these 2 yellow objects? So I can place it. If I put 1 there, I have 1 way to do it every single one. So there's 1 way to put it there. So if yellow 1 goes there, then yellow 2 has to go there. 1 way to go there, 1 way, 1 way, 1 way, 1 way, 1 way, 1, 1, 1, right? Wherever I put my first yellow one, so if I put it here, if I put the yellow one here, well, there's exactly 10 books, 4 books between them. 1, 2, 3, 4. Yellow 2 has to go there. Exactly 4 books. So there's 10 options. So 10 ways I can put yellow 1 and yellow 2, these 2 yellow, in which 1, 2, 3, 4, there's 10 options for me to put those 2 objects where there's exactly 4 between them. But I guess, again, we have to divide by 2 because it wouldn't matter if I put yellow 2 there and yellow 1 there, because we're over counting by, or in this case 5. So the ways that I can place yellow 1 and yellow 2 into these 10 slots where there's exactly 4 books between them is 5 ways. And then the rest of these books, which would be blue 1, blue 2, blue 3, for each of these possible ways, blue 1, blue 2, blue 3, red 1, red 2, orange, what's this? Orange, purple, green, orange, purple, green, 1, 2, 3, 4, 5, 6, 7, 8. So then this ways I can put times 8 factorial divided by 3 factorial, 2 factorial for the overcounting of these reds and yellows and blues. Yeah, I'm going to go with that. We'll check it after, but that makes sense to me. Divided by 3 factorial divided by 2 times 5. 16,800. Elisa selects 4 books from her 10 different books from the series. Find the number of different selections if the 4 books include at least 1 red book, at most 1 blue book, and exactly 1 yellow book. Okay, we're selecting 4. Okay, what different ways can this happen? So yellow, we have to have a yellow. And then we can have, include at least 1 red, so at least 1 red, and at most 1 blue. So at most 1 blue. So let's do that situation. Then we have 1 separate slot available, which could be anything. That's that. We have 4 books. So that's the first situation. The second situation will be, well, exactly 1 yellow book, at least 1 red. So at least 1 red, we could have what? We could have red and a red. We could have 2 reds. At most 1 blue. So 2 reds. Well, what about, we could have 2 reds and no blue, because it's at most. And the third could be, we have a yellow. We could have 2 reds. We have 3 reds? Yeah, we could, but it doesn't matter. At least 1 red. 3 reds. Red, red, red. At least 1 red and most 1 blue. We could have this. I'm just thinking of all the ways that we can do this. yellow, red, at most one blue. What else is there? Exactly one yellow book. At least one red, at least one red, at least one red, at least one red, at least one red. Exactly one yellow, exactly one yellow, exactly one yellow, exactly one yellow. And at most one blue. At most one blue. At most one blue, because we're picking anything in here. And at most one blue, at most one. Well, the last one, at most one blue. How many blues do we have? At most one blue, one red. So we're saying no blues here. No blues here. So this is going to be what? Let's just write this thing out again. We have blue 1, blue 2, blue 3, yellow 1, yellow 2, red 1, red 1, red 2, orange, purple, green. Red 1, red 2, orange, purple, green. So here we can select from 2 yellows to get this one. So that's 2 times, we have 2 reds, so times 2, times from blue, we have 3 blues, times 3. I'm just thinking, is there any other thing? Yellow, red, yellow, red, yellow, red, yellow, red, blue, blue. This is the maximum. Red, 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 blue, only one red. Times 2 times 3, and then from this last one, so the yellow is selected. So this is the scenario where we have 1 red and 1 blue. This is a scenario where we have 2 reds and 1 blue. This is the scenario of 2 reds and no blue. And this is a scenario where we have 1 red and no blue. And there's no other scenario which that would work, right? No. Yes. Okay, and the last one we're picking from. So we've taken this, taken these. So we got 3 left. So 3 options left. So times 3. So for this first one, we have 1 yellow, 1 red, and 1 blue secured. Then we have 2, 4. 4 times 3 is 12. 12 times 3 is 36. For this way, we have a yellow and 2 reds and no blues. Well, this will be 2 for the yellows times for the reds. Red 1, we have 2 options for red 1. One option? No, yes, one option. To pick these 2, it doesn't matter. We have 2, we just select 2 into it. So there's one option to do those 2 reds times. Then we have no blues, so then there's 3 at the end. So 3, right? 6 ways to do that. This one, 2 times 1 times. There's 3 options for that last blue. Be 6 as well. And this last one will be 2 times the red. We have 2 options, 2 reds, 2 options. Then these last 2, we have 3 times 3. 3 options. Then we've taken one of them. So we just looked at these because there's no blues here. Times 2 options to the last one. But then it doesn't matter if we pick like GP or PG. It doesn't matter. So we have to divide by 2 there because we're over counting. So that's going to be what? 4 times. So that's going to be 4 times. It's 12. 12, 24. 24 plus that is 60. So this is 60 ways. That's how I do it. I'm going to check it right now. Okay, let's go to the max screen. Okay, so the first one was 1,500, 151,200. Okay, that one is correct. Second one was 7,560. Correct. This one I'm not too sure about, but let's see. That one was 16,800, correct. And the last one was 60. Correct, 60. Oh no. Okay. Let's tick those back. God, I really do not enjoy doing this style of statistics. In fact, statistics actually, and the stuff that I'm interested in is actually very, very important. The statistical analysis that you have for quantum mechanics and basically all of like atomic theories, statistical analysis is very important. You have things like, you even have been introduced to Poisson, who's extremely important, like mathematically, for these things. So statistics is actually really important in in theoretical sense. But this kind of statistics, I'm not too sure about. I mean, this kind of like Elisa wants to pick different colors of different books. I mean, like, what kind of a question is that? Who cares? Anyway, there you go. I got everything right, so we'll call that 100%. Hopefully that was useful. I don't know if my explanations are that great, but I am trying to go through it in real time with you, showing you how you should kind of be doing it as well. So hopefully that was useful. And I want to say, in terms of mathematics, like, mathematics is beautiful. It is divine. It is incredible. It is so miraculous. Like, if you read and learn about the people who founded all of these areas of discourse which you find within mathematics, these people were highly intelligent people. They were almost divinely inspired to create such magic here. But the problem is this material has been heavily dumbed down and formulated into an exam to make it seem like very dry and uninspired. But in fact, this stuff is beautiful. And this beauty has been molded in a direction, I feel it even doing this, to where it's quite boring. I can see why people get quite disassociated with these subjects. But I'm telling you that it's not like this whatsoever. This is not what it's like. On the real level of sense, mathematics is a language of divine inquiry into existence. That's exactly what it is. I mean, it's an incredible gift that we have to be able to do this, but it's being repurposed in manners which I seem that are looking away from that gift. And that's because people writing these exams, people writing this curriculum, they don't understand mathematics to the level where this beauty is found. And so that's really the issue here. I will take it further with this stuff, but at this point, I'm just getting back into this stuff and reproducing content for you and helping you basically pass your exam and do very well in your exams. But I'm going to push more towards this other side of education, which is divine, beautiful, and inspiring. Anyway, I hope you're all well. I hope your studies are well. But that's it from me. I'll see you when I see you.